apologize, my camera ran out of battery, so I'll finish the rest of the lecture here. When we're talking about bending moments, the way that they are created is through some kind of a shearing. So when we're looking at a bending moment being applied to an actual material, let's say we're going to apply this one in, and using the right hand rule, that's going to go into the board. So we'll draw it in that configuration. We'll run that end. The other one will be here. This one here is coming out of the board, so we'll draw it in that configuration. This is the notation for coming out of the board. This is the notation for going into the board. We'll then draw this in the X and Y directions with Z positive coming out of the board. Okay? So this is what we're dealing with here. Now, just like what we did with the other two profiles, if we were to break this in the middle here and look at it so that it is broken here, we have this moment here, M. In order for this to be in equilibrium, we have to have an equal and opposite moment over here. Now, we don't have any loads, any net loads on this side, so we're also not going to have any net loads on this side. It's called pure bending. It's where we don't consider any of the other forces. We're trying to make it as simple as possible just for analysis. We're going to have an internal moment, and that internal moment has to be equal to M. Well, this moment is caused by intermolecular forces. Intermolecular forces don't actually have the ability to impart a moment on each other when they're just touching each other. That there are body ways of doing that, specifically magnetic or electrical ways, but quite frankly, we can't just exert a moment. So whereas what we saw in the axial load and the shear load, where it was just a summation of all of the intermolecular forces across here, we aren't adding a sum of moments. So what we see instead is that there has to be some kind of net moment, and that net moment has to be in the Z direction. Okay. Now, in order for that net moment to be in the Z direction, what we'll find is that there's going to have to be a push and a pull. So here, this one is causing that to be in compression at the top. So there's going to be a push at the top and a pull at the bottom. Okay. If that happens, this is a shear loading that is applied here on this cross section. And these two shear forces are going to, with the distance between them, some kind of Y distance between them, those two shear forces are going to result in a Z directional moment. And that one is going to be coming out of the board, so this is the correct way to draw this. So here's what we have. If we can do this kind of configuration inside of this beam, we can get a moment. And that shear loading is going to produce a moment because the forces are separated by some distance y. Now, it isn't just going to be that we only carry load on the top and the bottom. It turns out that if you look at the actual profile, unlike the axial loading where it was constant across the entire interface, this one's actually going to decrease in value until it reaches 0, and then it's going to switch back the other way. And so you get this triangular trajectory for all of your loads, where all the ones on top are going in and all the ones going down are coming out. And if you sum all of these, you get a net force in that direction, and if you sum all of these, you get a net force in this direction, and then the total moment is going to be the difference between these two. Well, why do we have a 0 point? Where's that 0 point at? Well, here it is actually on the axis. It's not always going to be true, though. This part of the cross-section, if we look at it on an end-on view, this part of the cross-section is right here. That is a centroid. And we're looking at basically a dotted line here that goes through the centroid. This defines basically the center of the beam. Now the centroid is dependent, it's a geometric property based on how much material is above and below the centroid, trying to find the average center, so to speak. So in this case, what we have is that this area up here will all be in compression, and this area down here will all be in tension, with the maximum tension occurring at the very bottom and the maximum compression occurring at the very top. Okay, and that would work well if it's a rectangular beam. If it's a circular beam, same thing applies. Your maximum compression is going to be at the top, and the maximum tension is going to be at the bottom. Okay, but we can look at another shape. We can go ahead and look at a T shape on this. Now if you look at a T shape, the centroid on here is not actually in the center. It's closer to the middle of this larger beam. Okay? So if we look at something like that, here your stress distribution is going to look something more like this. This is going to be your 0 point because that's your centroid. And you're going to see very large forces up here and then much smaller forces down here. Now that said, the largest stresses are actually going to be located here. Even though it's a smaller amount of load, you have a larger displacement that ends up getting carried in order to cover this weird difference. Because, as you remember, our equation is sigma is equal to my over I. Well, this has the largest y value because here, y value is the distance away from the centroid along the y-axis. Okay? So now the whole point of this is trying to figure out what direction is our normal force actually exerting in. So we take a look back at this. Here, if we break this cross-section in the middle, it is applying a net moment across the entire section. That net moment results in a striation of loads where we have larger loads at the top, larger loads at the bottom, and those loads will sum to create shear loads. So we have shear loads, net shear loads, acting between the two top and bottom of interfaces of this, and that creates our moment across our cross-section. Now, even though these are shear loads, these shear loads are acting in the x direction. And you'll notice that's also the axis of our system. So here the rule that we have generally when it comes to bending is moments, I should say bending moments. Bending moments create stresses, and these are normal stresses, in the direction of the axis. Now it does actually generate some shear loading that's perpendicular to the axis. Yes, that is true, but those shear loads are much smaller in scale than the bending loads themselves, so we don't usually consider them. We focus mostly on the bending loads. Okay, so example, if I apply an MZZ moment, this with an axis along X produces a sigma X stress. Okay, so here what we would see is all of these are sigma X's. Okay, and so that's the bending moment. Now let's cover torsion real quick. Torsion is a little weird because if you look at torsion, it doesn't quite make sense directly. Here, the way that we signify torsion is, if I were to draw it on the end, here's a torsion that's coming out of the plane. Well, the counteracting torsion to that is going into the plane and it happens to be on top of it. So they're kind of lying on top of each other. As I mentioned, these are two moments that are on axis with each other, so they do overlap. So we have to find a different way of signifying them. And the way that we do that is we have a double-ended arrow. Now here, double-ended arrow indicates direction using the right-hand rule, so you would expect it to torque in this direction on this side, and then it's torquing in the opposite direction on that side. So those two are going to be balanced. Okay. Now, when we're looking at this, oftentimes you're only going to evaluate torsion on a circular interface or on a hollow circular interface, because the torsional stresses get a little weird in a rectangular shape. It doesn't quite follow the equations that we have. But when we're looking at this, if we go ahead and break this again at this interface, you have your torsion over here, you have this piece, and then this has to carry a net torsion, which is equal to that, in order for this to work. Now that net torsion has to be carried along that face and has to be carried along the intermolecular bonds on that face. So we do run into a little bit of a difficulty here because, again, intermolecular bonds are not capable of producing a moment. What is capable of producing a moment, though, And what we see is that it actually exerts a load around the outside of the object. Well, it's not just the outside, it's actually concentric bands where each one of these gets smaller and smaller and smaller, the actual loads. Loads increase the further out radius we have from the center, but all of these loads point in the same direction. And the cumulative of all of these loads acting contributes to one net torsional moment. Okay? Now, when we're trying to figure out what is the actual axis for this, let's go ahead and say this is the XY axis. Let's go ahead and say then that this would be the YZ axis. We'll say Z is going this direction. Okay, so if we pull out just this element, we have this curved element here. We'll call it a unit cube. We know we have a net load up here on the top of this item. This net load is acting in the Z direction on the Y face. So since that's the case, this is a tau YZ. We also know that since this is a shear load, a shear stress, because it is parallel to the face it's acting on, we're also going to have additional shear stresses that arise in all of these. And what that's going to do is it's going to cause the element to twist in that way, which is actually where we get the iconic twisting of a torsionally loaded member. All of the unit cells look like this. So we have tau YZ here, tau YZ here, tau YZ here, tau YZ here. Okay. Now let's go ahead and look at this one down here. Here we have a downward facing load. Well, this is in the negative Y direction. Okay, and it is acting on the Z face. So this also is a tau YZ. And since we know that this is a shear stress, there's going to be an equal ones here. And you'll notice that these two elements are exactly opposite of each other. Here and here they're different. But if you were to rotate your camera, this one becomes this one. You know, you rotate and go down here, this one becomes that one. You rotate and go over here, this one becomes that one. They're all the same. They're all working in the same orientation, although this one's... It's all just a rotation here. Now what we don't see in any of these is we don't see any x-directional stresses. I had a student bring up in class, but there should be some x-directional stress, and there is, because there's actually, as you twist it, it causes a compression in it. It pulls it in on itself, which causes it to elongate a little bit. However, the elongation is pretty small, usually, so we typically ignore it because it only really becomes in play when you have a firm boundary on both sides of the rod, so it's not allowed to elongate, which is also poor design practice. So we don't usually deal with an axial load when it comes to torsion, even though there is some elongation in that direction. But what we see here is the general rule of thumb when it comes to torsional loading is that in torsion, a moment produces a shear stress that is not along the axis. So as an example here, we have TZZ that was applied. Oh, I guess that's TXX. My apologies. TXX with an axis along X produces tau YZ. So even though tau Y doesn't really get brought in here, because it's a part of the cross section, and because it is in the plane perpendicular to the x-axis, that's why we're seeing that. Yeah, so that's what we discussed in class today. We will continue this discussion, do some example problems over calculating bending loads and torsional loads in advance of the assignment for next week. Get ready for your vocab quiz on Wednesday.